Hello everyone, my name is Kanga Trevor Joel and I'm presenting on behalf of group SWML8. My group mates are Akanga Andrew and Okanya George and we are supervised by Dr. Marvin Galiwango. Our project is called a dual model convolution architecture for real-time hospital navigation. You can call it the HospiNav. So this is a real-time autonomous wheelchair navigation system for hospital environments. So this is what we will go through. An introduction to our problem, related work, a problem statement, research questions and objectives, research contributions, methodology, our dataset description, results limitation, and the conclusion. Related work. These are the papers that have something similar to what we are doing. The first one is attention is all you need. In this paper, self-attenuation was established self-attention mechanism. But the issue with it is its quadratic complexity makes it unsuitable for real-time edge devices. Because for us, we are supposed to put our system on an edge device. So that was the structural limitation. The second one was the single-shot multi-box detector. Now, this introduced multi-scale single-shot detection, which is fast, but its issue is its performance on very small objects is really bad. And the most directly relevant paper is by Quadri and Jawawi in 2024. This specifically looked at wheelchair navigation in hospitals. They found the yellow R to be suitable for safety criteria, but it failed to meet real-time execution requirements on its own. That finding directly motivates our dual model approach. The other paper was the HIOD dataset in 2023. This had very strong accuracy, but it covered 56 generic object categories without any navigation integration or person annotation strategy. The gap is exactly what we are feeling. The scale of the problem. 65 million people worldwide need wheelchair assistance. In hospitals, the assistance at the moment is manual, where you're having a member of staff, let's say a nurse, gets to push the wheelchair around in the hospital. Well, the issue with this is that this reduces the clinical capacity available for patient care. Now, the hospital is one of the most complex navigation environments because equipment moves constantly, staff and patients appear out of nowhere. And the current automated systems fail to handle the density, diversity, and the dynamism in such environments. The objective of our project. Now, our objective is quite simple. Now, we're taking a camera frame, we detect obstacles in that frame, plan a safe path, and output a drive command. That is the full loop.
Hi, my name is Akangandro, and I'm going to be taking you through the methodology and system architecture. So our system is divided into 5-station navigation pipeline. So the first one is the the first station is the yellow V8. So the yellow V8 is going to identify the objects that are in the frame. So it's going to see this is a person, this is a seat, and so on, all the objects in that. So the second stage is the depth instinct version, which gets the depth per pixel and draws a map, a heat map. You're going to see it in the later slides. So that heat map estimates the distance between the webcam and the person, or the wheelchair and the object. So stage 3 is the occupancy grid. So this occupancy grid is going to get the yellow V8 and the depth heat map outputs, and then converts them so that it can draw a 20 by 20 grid, which shows the start position and the end goal where the planning is going to happen. So the fourth stage is the ESTA planner, which tries to navigate through the obstacles as identified in the 2D map. And then the last one, stage 5, is about giving you the action to take. Go forward, left, right, or just stop. So yeah. So next, we're going to be going through the model architecture and the mathematical foundation. So you're going to start with the class focal loss. Sorry, where's the pointer? So you're going to say that the class weighted focal loss is, why do we need this? Our model has a class imbalance of 19.2 to 1. So this class imbalance is between the monitor and the bin. The monitor has almost 594 annotations in the dataset, but the bin only has 31 datasets in the annotation. So with this imbalance, the model, without intervening, the model will learn to ignore the bin entirely since it doesn't contribute to the total loss. So what we do, we are going to come up with a focal loss formula, and we used a 9.7, which is almost, we just divided 19.2 divided by 2. We first made some experiment, and this is not a guesswork, so to solve the imbalance in this work. So yes, so that's why the focal loss to solve the imbalance. The second one was dual head and fusion. So that architecture, we said that if we only train one head of yellow V8, it's going to be catastrophic forgetting. So how are we going to solve catastrophic forgetting? Because it will unlearn to detect the person class. Remember, our dataset doesn't have the person class, so it might unlearn to detect the person class. So what we do, we are going to use two heads. The first head is going to be fine-tuned on our A equipment classes. The second head is going to be we are just going to freeze it, and we are only going to be using the person class only. So with this, we are going to be able to navigate more that thing of the missing class of the dataset. So the second mathematical foundation we used was Hamilton distance, where we are drawing number of rows and columns. When you are using extra, we did not use the other distances, but we try to use Hamilton because we are going to be using a grid, so there are no distances across. So this is our equation for end-to-end, which takes in the grid, the depth, the objects detected, the fit, and everything into consideration. So in results for this experiment, we got a mean average precision at 0.5, which is 83%, and a recall of 0.78, 78%, and yeah, and the person class had an accuracy of 0.7, yet when it was around, was really detecting it. Yeah, thank you. So this is our dataset that I was talking about. It's called Hospital 314 RIU from Lobo Flow. It has 1,457 images and 241 annotations. It has 8 object classes, and this is its split. We kept the split and we did not use random splitting because since this wasn't a video and they just got images from Google and then they just annotated them without breaking them. It wasn't a video. That means that random sample edge splitting won't happen because they won't be transferred priming of the environment. So as you can see, this is how it's split: the test, the validation, and the training annotations. Yeah. So we are going to go to findings of our EDA. So what we do find when we did our EDA, the first majority thing we found out that is when you look at this bounding box center heat map, it shows that there is a center bias in our dataset, and in the middle of the frame, as you can see, it's very bright here because most of the annotations, their centers are here, but there's barely anything above this point. That means this will lead to annotation sparsity. So it will cause the model to not perform very well in areas that are on the edges. So that's one of the problems that we identified in our dataset. So continuing with our findings, you are going to see that most of our images in the dataset show that most of the objects cover half of the what? Half of the frames. That means it shows the your density of a hospital, because you're going to find whenever you're passing by a hospital, you're always going to find one of these objects. You're going to find a person, you're going to find a chair, you're going to find a stand. So it shows the the complex of a hospital. But the downside is that we have shown that the distribution of the annotation count per image, that how many annotated counts are there in each image. We showed that most of them are here in most of the images only have one annotation, which doesn't show the full complex, because you're not going to only find one object. When you are driving through a hospital, where you're going to find more and more images. So this is also a downside of our dataset.
My name is Dr. George, and I'm here to continue from where my colleague stopped. So for the current slide, we are going to talk about the ADA findings and the gap analysis. So to begin with, the most important finding we had was that there are 5 classes that are completely missing, and they're important in navigation. And in this case, we have the corridor signs, the trolley, the wheelchair, the door, and the person. And then on the 8, we have the 8 that have been stated throughout this whole series. We have only the monitor, the bed, and the sofa that meet the 300 annotation threshold for reliable detection. Focusing on the person class only, the gap directly motivates a dual head architecture, which we have chosen in this case. And uh, no annotations, it means that the fine-tuned model will never learn to detect people because we lack the person annotation, sorry. So in this case, we're using the frozen cocoa head, and it solves this at 0 additional annotation cost. Next, we're going to discuss the output results, and yeah, we're going to discuss the output results. We're going to look at the validation and training. Here you look at validation, mean average precision at 0.5 per epoch, and validation recall per epoch. Then for training, you look at the training box loss and the training classification loss. Yeah, these are the training curves, and they show 3 experiments, which are baseline, weighted, and augmented. Baseline and augmented both converge, so you see that both baseline and augmented converge quickly at near 0 classification loss. The augmented experiment starts with classification loss of approximately 75, and this spikes. Yeah, and that spike there of 75 is caused by mosaic augmentation, combining 4 images per sample. Yeah, that's for training. It descends to around 10 by epoch 50, but it has not fully converged. Augmented needs more 50 epochs to converge. Yeah. Next, we look at the validation curves, which are these ones. They tell the selection story. The baseline peaks at mean average precision of 0.87 around epoch 36, but each recall is only 0.71. So the weighted and augmented plateau at MAP 0.83. You look at 0.83, you look at the plateaus there, but both reach the recall of 0.787. That means we are trading 0.035 mean average precision for 7.7 percentage points of recall. Given that a missed obstacle causes a collision, the trade-off is non-negotiable. So here we really look at more recall than precision. Let's look at the results per class and ablation. So we have a confusion matrix which confirms the pattern. Strong diagonal across sofa, bed, and monitor, which are the well-represented classes. The dominant failure mode is the background row. Objects predicted as background rather than their correct class. That is the dominant failure mode. That is caused by the spatial center bias. Objects near the frame edges or floor levels are underrepresented. Most of our images are in the center. The bin gets one correct prediction and one background prediction on two total validation instances. That result is statistically unreliable but consistent with the 31 instance training class. It is a data problem in this case, not an architecture problem. Even GradCam confirms this. The monitor produces a tight focused heat map. The bin produces a scattered diffuse one because it's a small object and it's a bit to the edges. The ablation study quantifies the interventions, and without the bin class weight, bin recall is next to zero. Without the dual model setup, the person in average precision is 0.04, and both interventions are necessary and their effects are independent. Now we have a demo of the developed product, and that video will also be posted with our submission. But this is just a small overview and a small something brief about how it works. So the full pipeline is deployed as a Flask web application on Hugging Face spaces. The browser, in this case, here on Start Webcam, captures a frame. It encodes it as a base64 joint picture expert group, that is JPEG, and sends it to the server via the post to an endpoint called the process frame in our application. The server runs at all 5 stations and returns the detection image, the depth, and the map. You can see this, the detection image, what it has detected, the depth field, and the map. In this case, then also the occupancy grid with the star path role. In this case, you can see a path because there is weather, and the drive command. The drive command is, are we going forward, left, or right, or we stop? Everything here runs in a Docker container with pin dependencies for reproducibility. The repo is also given in our research paper, in our concept paper, sorry. So other models that we tested, we have type A and type B, and in type A we trained them from scratch. Type B they were pre-trained. So from track A from scratch, the yellow V1 failed due to a coordinate decoding bug, and 7x7 grid limit with one detection per cell. The vision transformer, the VIT here, was actually the best in track A at precision of 0.619, but required 150 epochs and had no pre-trained weight, so it's not practical. The SSD collapsed entirely with a precision of 0.003 due to anchor scale mismatch, and the detection transformer, the DETR, from scratch reached an F1 score of 0.459 at epoch 5, then suffered a query collapse. Recall dropped to 0.014 with this one by epoch 100. Then in type B, we had the pre-trained models, and the faster recurrent convolution neural network hit a mean average precision of 0.785, but only at 10.5 FPS, which is too slow for edge computing. We also had a pre-trained DETR, which got an MAP of 0.564 after 3 epochs with 0 bin detection. We also look at RetinaNet, and our RetinaNet got an MAP of 0.816 and at 86 FPS, but its recall was 0.740 versus our 0.787 on the yellow V8S, and it used no bin class weight. We also had we had a 37% bin average precision. So in this case, the yellow V8S, the weight wins at every safety metric, of which our problem really prioritizes safety. So a conclusion and the next steps we have for challenges and for solutions. We had the class imbalance problem, which was solved by the 9.7 times focal loss weight. That's where the bin with its average precision from near 0 to 0.512 using the focal loss weights. Then a 0 person orientation solved by the dual model architecture, where the person recall comes up to 0.71 versus 0.04 in a single architecture model. Then edge deployment constraints addressed by int8 quantization, targeting sub 100 millisecond latency, and safety prioritized by calibrating for minimum false negatives. Phase 2 targets, what's next? We're looking at the depth floor to replace the depth anything version 2 for metric depth in real meters, then the Jetson Orin Nano with a tensor RT for hardware validation. Yeah. The semi-supervised pseudo labeling to grow the training data for the missing classes, and that is for future work. We would like to accumulate some of the references we used, and we use the XAI technique. Our reference is given completely. We look at the semi-supervised expansion, which is our phase 2 plan, and the related work that for datasets and navigation systems, all that is given.